In year one, we solve linear programming problems using a graphical method, which I'm going to demonstrate now in example 4. In fact, we're not going to actually solve the problem in example 4, we're just going to show how we set up the graph, which we will go on to use to solve it later. Right, so the problem we've got is that we're trying to minimise these, they're probably going to be cost that's equal to 0.5x plus 0.4y. So saying x costs 50p, y costs 40p. And we've got subject to those constraints, x is less than y, 2x is less than or equal to y, 3x is greater than or equal to y, 3x is greater than or equal to 2y, x plus y, the total is greater than or equal to 60,000, x comma y is greater than or equal to 0. Now, whenever you have to solve a problem using a graphical method in the exam, the scales will always be drawn for you because the examiner wants to see exact identical graphs each time, as it makes it so much easier to mark. So you'll probably need to decide though what scale to use on your graph. So use a nice simple scale. Now from x plus y is greater than or equal to 60,000, I know I'm going to need to go up to 60,000 on the x and y axes. Rather than writing 10,000, 20,000, 30,000, I've just written 1, 2, 3, 4, 5, 6 in the scale, x, when the label x, and I put in like 10,000s, y in 10,000s, just saves writing it all out. Here, the non-negative clause means we're going to be in this quadrant here. There's going to be no negative for x and y. So what we first need to do is draw lines for each one of the constraints. I would always write y first. So I've got y is greater than x. Y is greater than or equal to, actually, less than or equal to 2x. It points towards the y. 2y is less than or equal to 3x. In which case I can make y is less than or equal to 1.5x, and that's fine as it is. Okay, so let's do them in turn. We're going to need to wait to distinguish between greater than and greater than or equal to. Now, you will have learnt that at GCSE. When you're doing a greater than or less than, you use a dotted line. When you're doing greater than or equal to, less than or equal to, you do a bold line. And in almost every single exam question, it will always be or equal to, so you'll be doing bold lines. So what we need to do firstly is equate them and draw the lines of the equation. So like y equals x, y equals 2x, y equals 1.5x. So we're going to start off with y equals x. Well, if y equals x, when x is 1, y is 1, when x is 2, y is 2, when x is 3, y is 3, you get this diagonal line. Remember though, I need it to be a dotted line. So 1, 2, 3, just put a few dots in, so you see you're going through the corners of the squares. Have a dotted line. Y equals x. Now we're told y is greater than x, y is greater than, y is bigger than, y is above. So we can be above this line. So I'm just going to put some shading marks below this line. Which indicates our solution must be over here somewhere. Looking at the second one, I need to draw the line of y equals 2x. You've got loads of different methods for drawing straight lines. So you could use y equals mx plus c. So y equals 2x plus nothing. So the gradient is 2. So that means 1 across 2 up. And that's the intercept on y-axis. So it's going to go through the origin. So going through the origin, it's going to go 1 across 2 up, 1 across 2 up, 1 across 2 up, and so on. You can put some points in. If you're drawing a straight line, you just need 2 points. It's often a good idea to do 3 points, just do 1 to be on the safe side. So x, y, when x is 0, y is 0, when x is 2, 2 2s are 4, y is 4, when x is 4, 4 times 2 is 8, and that would actually disappear off the graph. But you've then plot them and join them up. This one will be a bold line because it's all equal to. And we're saying y is less than or equal to, but less than, smaller than, below. You're smaller than something, you're below it. So we shade above it. y equals 2x. So this indicates our feasible region where our solution might lie will fall between these two lines. Next, y is 1.5x. So that means we're going to go through the origin because plus c 0, and we're going to go, the gradient's 1.5. So that's 1.5 over 1 or 3 over 2. So up divided by across, we can go 3 across, 2 up. No, sorry, 3 up, 2 across rather. 6 over 4, 4 across, 6 up. Or you could do 1.5 over 1, 1.5 up, 1.5 up, 1 across. Or we can plot some points in the same manner we did here. When x is 0, y is 0. When x is 2, y is 3. When x is 4, y is 6. Again, this is a bold line because it's all equal to. It's less than or equal to, so y is smaller than, y is below, it's lower than it. So we just put shading marks above it, which has narrowed down the feasible region to just this triangle here. Which actually makes this constraint a waste of time, because if you're obeying this constraint, you're automatically obeying this constraint. You can't be less than or equal to 2 if you're also less than or equal to 1.5x. Okay, the final one, x plus y is greater than or equal to 60,000. To do that, we're going to work out where the lines will cross the x and y axes. When x is 0 along the y-axis, y is 60,000. When y is 0, x is 60,000. So actually, just use a simple cover-up method. Y is 60,000, x is 60,000. So that tells you where it will cross each of the axes. So 60,000, 60,000. Okay, it's a bold line. Try to make these graphs as accurate as possible, because you may need to use them to read off a solution. And the more accurate you do, the more accurate the solution will be. Alright, and it's why when you're looking for where to do your shading, you only need to look at the y and the inequality, providing it's plus y. If you've got minus y or minus 2y, stick it on the other side of the inequality and make it positive. So when you've got a positive y, just look at that bit. Ignore the x, ignore the numbers. Positive y is greater than, y is greater than, y is bigger than, y is above. So we need to be above this line, so we shade below it. So using all those constraints, that tells us the feasible region is here. Our solution lies somewhere here. Now, we may be able to have a decimal solution. We may only be able to have integer solutions. We'll come on to it later, but say, for example, you can only have integer solutions. You could have a solution, say here, x is 4, y is 5. That's a possible solution. Here, x is 3, y is 4. Now, you couldn't have this solution here, x is 3, y is 3, because you couldn't lie on this line. You can lie on the bold lines, you can't lie on the dotted lines. Okay, but there's obviously an infinite number of solutions because this graph carries on forever. So that's the only example on this exercise. If you can have a go now at exercise 6b.